you so much for the introduction. Um, yeah, thank you so much for inviting me. Yeah, I'm Jeremy Dow. I'm from Oregon State University, part of the Dynamic Robotics and Artificial Intelligence Laboratory, or DRL for short. We recently underwent a bit of a name change. If you guys have been reading some of our work, you might have known that we were just a DRL, but we kind of recently stuck in that artificial intelligence in there, mostly because it's actually really relevant to just what we've been doing. And so for the past 4 or 5 years or so now, we've been really focused on applying reinforcement learning for bipedal locomotion. So what I'd like to talk about with you all today is just sort of the journey that we've taken with that and all the things that we've tried, things that we found to work well, and just sort of share our work and our experience with that. So just to provide some context, we're primarily focused with the robot Cassie. It's actually the only robot that we have right now, which is mostly just a pelvis and 2 legs, weighs around 30 kilos, 10 DOFs. We have 5 motors in each of the legs, with just 1 degree of freedom at the toe, and then also has 2 springs, 1 at the knee, which is actually hidden under the shell here, and then 1 at the tarsus. So I guess, one of the first questions that we might ask is why use reinforcement learning at all? Since, it's definitely not needed. Cassie can walk and walk pretty well already without learning, using all the model-based and MPC stuff that people have been using for a long time. And so, using just reduced sort of models, some planning, some optimization, Cassie is perfectly fine, walking up these small steps and walking around pretty robustly. But we like to say that reinforcement learning is really good at sort of getting into the corners of the dynamics. And so these data-driven methods, through tons and tons of experience, we think can produce, it's a lot easier to produce really agile and much more dynamic behaviors. So like a little sneak peek here, Cassie's running at just under 4 meters a second here. And we think we'd struggle a lot to get this kind of behavior through model-based methods alone. So how can we use reinforcement learning? Well, I'm sure, as Xiaoming talked about earlier, and as we've kind of all seen this general loop of RL, where, we have some agent, which is some neural network policy or something that takes in a state and produces some action that it takes into an environment, and the environment spits back out some reward that tells you how good you're doing. And then also a new state, and you keep going back into this loop over and over again. And by collecting all of this data, the policy will magically figure out how to produce better actions that you will get higher reward. And so, for reinforcement learning, like pure people and the theorists, this is it. This is set, right? You're given your Atari game, your OpenAI gym environment, whatever. You handed this problem, make an algorithm, reward go up, big number is good. But we're roboticists. We kind of, that's not what we care about. We approach things a little differently. And so what I care about is I want to make Cassie walk and do really cool things. So how can we do that? So really we have we have the ability to sounds good. Thank you. We have the ability to sort of make all of these design choices about every single part of this, of this RL loop. So, we have control over what kind of form or structure is our policy going to take in terms of our action. What actions is our policy outputting? Is it doing torque control, or joint position control, or maybe trying to learn footsteps? We even have control over, what we're setting the task, or are we trying to learn to walk or to hop or to do what? What kind of environment is it learning over? Are we learning over flat terrain, noisy terrain, whatever? Maybe we're even learning over multiple different models or environments. And then probably the biggest and most difficult one is the reward function. Like, how are we going to reward the policy for doing the right thing? That's kind of sometimes exceedingly unclear, but we'll get to that. And then you also have, control over what are you going to call your state? What sort of information are we going to pass as input into the policy? So I would just like to share through just a multitude of overview of all of our works that we've done recently and all of the different kind of changes and design decisions that we've made to each part of this loop. So we'll kind of keep coming back to this image. So I think, yeah, the biggest question that usually comes to mind is what should the reward be, right? If we want Cassie to walk, how are we going to define that? How do we, mathematically get in one number that says how good are you at walking? And so, the really naive approach is say, let's just move forward. I want Cassie to match some speed, so do that. But if you do that kind of really naive, underspecified reward, you kind of get, this really weird idiosyncratic behavior where, the agent is satisfying that reward, it is moving forward, but because that's all you told it, that's all it's going to do. And you're not really specifying how it should do that, when in reality, you actually have some goal of how it should move in mind. As Xiaoming actually already talked about earlier today, our first attempt at this was just going to say, okay, well, let's just show the agent how to move. So we're going to start with this reference trajectory as kind of the seed of like showing the policy how it should achieve this task. So this is just, one full order reference trajectory that we have. And we're just going to ask the policy to basically try and mimic this. So yeah, some of our first work, actually, John, we already talked about a little bit this today. It was basically first following this setup where a reward function is just to basically at each time step match the corresponding position, full joint position of the reference trajectory. And we're actually able to get things to work pretty well. And even though we only have one trajectory for walking at a certain speed, we can actually generalize to walking to different speeds just by sort of stretching or shrinking this trajectory down, which basically means just literally translating the center of mass motion. And so, of course, when we do this, the trajectory no longer becomes dynamically feasible at all, but that's fine. And so even though the feet are kind of sliding along the ground, it's a good enough learning signal that the policy can kind of fill in the gaps, which is, another really great benefit of these data-driven methods. So kind of going back to this, exploded image, we just started with a really sort of simple setup. We just had a regular 2-layer feed-forward neural network. Action spaces, we were learning basically residual joint position targets on top of the reference trajectory. We're kind of just learning some feedback around that nominal trajectory. And then we can generalize to walking over different speeds, both forward and backwards, along with some speeds sidestepping, and basically just train on this single model on flat terrain. And the reward is we basically want to track this reference trajectory. And we kind of take this iterative design approach where you just, train a policy, see how it looks. Things are a little funky. We kind of add some heuristics on it to make it a little better. So for example, we first trained a policy to just match the reference trajectory. We found that things are kind of a little shaky, not so great. So we add some heuristics to like minimize the pelvis rotational velocity, minimize joint accelerations. And then we found that, okay, that helps, but then now our policy is kind of a little stompy and it makes really aggressive motions. So we had another heuristic to kind of penalize the applied foot force, and then that works. And then we find that when we do that, the feet don't lift up quite as much anymore, and so now it becomes less robust. So we can add in another heuristic that ask the feet to lift above some minimum height. So this is one of the not so great parts of RL, was you're not really always sure what you're going to get. So you kind of have to rely on a bunch of design. But we'll get to possibly solving some of that as we go down. And so sort of the next step that we took was adding more reference trajectories. So, our previous work, we just kind of had this one reference trajectory that we were going to, stretch and shrink to match the different speeds. But then we thought about, what if we had a whole library of trajectories? And so we can better match, because we found that as we tried to do behavior that would deviate more and more from our, one reference trajectory that we had, we would sort of lose information, because we just weren't as successful because we're kind of deviating more and more from this reference that we're learning around. So we decided to first optimize a whole library of reduced order model trajectories for sort of like little speed increments from like 0.1 meters a second all the way to 2 meters a second, and then pretty much followed the exact same framework as before. And so, and we found that, you know, this works as well, but we also able to get really cool behavior out of it because we were trying to match this like reduced order model, this actuated slip trajectory. We found that the behaviors that we were getting out of it would also start to really mimic that motion as well. So you can see both in like the animated reduced order model trajectory kind of matches the simulated trajectory that we learned in simulation, and then even matches behavior that we get on hardware. And so not much has changed. We kind of just are following the same formulation, but, you know, we now have this whole library of trajectories. And then also the trajectories are no longer full order trajectories. Now we have this reduced order sort of task-based trajectories that we're trying to match, which we also found to kind of help in the sense that we're freeing things up a little bit. We were kind of worried that, you know, trajectory tracking is a little bit restrictive, and that you're really specifying, or you're really asking the policy to try and match every single joint, match along the way. When really, you know, we kind of don't care about that. We're kind of just caring about the motion, the footsteps that it's taking, and the motion of the center of mass. We also found that before we were kind of actually inputting the reference trajectory information into the policy, because we were thinking that, you know, that's going to be really useful since that's what it's trying to match. But then we actually found out that that's actually not useful at all. And all the policy was seeing it as is this kind of cyclic clock signal. And I was just seeing, you know, this repeated set of, you know, this repeated 20 long vector or whatever every single time. And that was just acting as like a cyclic clock. So we thought, okay, screw it, then we don't need to input that. Take that out, replace it with just, you know, two numbers that's going to replace a cyclic clock. And things work actually much better. And it's actually really important to sort of have this really cyclic regular input, because then that really makes sure that what you get out of the policy is going to be very regular and cyclic as well. And that really helps a lot in preventing those kind of really weird motions that you would see if you had a sort of naive setup. And then the next sort of design choice that we were looking at was the policy structure. So before, what we've been using was mostly just really naive, you know, vanilla feed-forward networks. But, you know, the system is a lot more complex. And so, you know, there's a lot of states going on. There's a lot of unobserved states in our system as well. So we're looking at starting to use these memory-based networks or recurrent neural networks that basically are they pay attention to the past states as well. So they sort of have like a memory to them. And through that, you can get greater representational capacity. And we're hoping that that capacity to memory would help a lot with learning better policies. And so we found that, you know, switching to these kind of recurrent neural networks produced much more robust behaviors, since they kind of had, you know, greater representational capacity and could, you know, actually learn things about the state that we weren't specifying. But they also had some minor drawbacks as well, and the fact that they changed how we would have to starting to deal with the sim to real transfer. RNNs, because of the greater representational capacity, also have a greater tendency to overfit. And so we found that they would overfit more to our single model. And so because of that, would actually have lower rates of transferring from simulation to reality. And so we found that we had to sort of solve that by using dynamics randomization, which is a very common sim-to-real technique in reinforcement learning, where you're basically doing training, randomize a bunch of dynamics parameters like joint mass or damping or the ground friction. And you basically end up training over a distribution of models. And ideally, the true model is somewhere in that distribution. So if you learn to be okay on this distribution of models, you know, when you transfer to hardware, you'll be fine as well. And so we found that whereas this wasn't necessary for the feed-forward networks, this was for these memory-based networks, which was, you know, interesting to see. So yeah, going back, you know, now we're going to change our policy structure from regular sort of vanilla feed-forward networks to recurrent networks. And we're going to change our environment in that we're starting to use dynamics randomization. So we're now kind of training over a whole multitude of different models instead of just one fixed model. And then another small change that we made to our action, we're still using this sort of reference trajectory-based framework, but before, whereas we were outputting residuals to the reference trajectory joint positions, we now sort of output residuals just to some sort of constant neutral offset. So we're no longer learning about the reference trajectory, and we're just kind of learning about some fixed position. And again, the idea about this is we were sort of worried about restricting the policy to only exploring around the reference trajectory, and so we were trying to free things up. And there's this general trend of trying to get rid of as much reference information as possible. And so the last bit of getting rid of that would be in the reward. And so we really wanted to, get rid of this reliance on reference information. But if we take that out in the reward, then it becomes like, how are we going to reward walking? And we came up with this sort of periodic reward structure that will basically specify when each foot is supposed to be in swing or stance, and it incentivizes things accordingly. So if we want a foot to be in stance, we will penalize foot velocities. And if we want a foot to be in swing, we will penalize foot forces. And basically by, so we have these periodic clock functions that will specify for each foot when we want to penalize foot forces and thus be in swing, or when we want to penalize foot velocities and thus want to be in stance. And by basically changing the shape of these clocks, we can actually then specify any bipedal gait that's possible. So you can see as these, sort of forms shift, you can see the corresponding behavior in the feet change. So, as an example, when these are perfectly out of sync, we get something like walking. So, when the left foot is in swing, then the right foot will be in stance, that's walking. But then if we shift those to be completely synced up and to be in stance all the time, we can actually also specify things like standing. Or if we sync them up but still have this, going back from swing and stance, then that's something like hopping. And all of these parameters are just continuous parameters that we can change on the fly. So the things like the ratio between swing and stance for each foot, stepping frequency, sort of the difference, the phase offset between the left and the right foot. And by just changing all these continuous parameters, we can, on the fly, command any bipedal gait as well. So you'll see here, Jonah in the background is holding a controller, and on the controller, there are just some knobs that we have to change these parameters. And so we can smoothly transition from walking to hopping to these kind of galloping behaviors. So now we've changed our reward to no longer be reliant on this sort of reference trajectory information. We now have come up with this kind of generic periodic reward that we can use to describe any bipedal gait, and it's just sort of based on, the timing of rewarding swing or stance for each foot. And so now we're no longer restricted to just training on walking and walking at different speeds, but we can now train policies that can do sort of all sort of bipedal gaits. And then next we were sort of looking at changing the task that we're training over. So previously, all of our policies have really been conditioned on speed. We're asking Cassie to match some speed of, like, let's say 1 meter a second. But then we were interested in looking at things like footsteps. So, we can navigate difficult terrain and step over gaps. So basically all this is basically the same framework, but we add in an extra reward component that is penalizing or rewarding the policy for matching some desired footstep location. And we were able to sort of just using minimal perception, just having this overhead camera, so we can get this feedback loop on where Cassie is actually placing the foot. And we can, using this way, we can realize a multitude of different sort of footstep patterns and get behaviors that we were not able to specify or generate at all before with our speed-based policies. So here we can sort of take really sort of irregular steps of like one long footstep followed by one short footstep, as well as varying the direction as well. So again, mostly minor changes kind of following the same framework, but building on top of it again and again, using the same kind of reward, but we now have this extra reward for matching a specific footstep target. And instead of training on different speeds, we're training over a range of footsteps. So training over this range of footstep lengths and direction. And then since we had all this work on coming up with this framework and it seemed to be working really well, we decided to take a look and see, well, how well does it really work? We started to think about how can we push the limits? How far can we go with this? So we started to look at using that framework to generalize to walking with different kind of dynamic loads. So here we have a number of different loads, and we found that just by sort of showing the policy in training of these loads, for example, like a loose box on top of a tray, or Cassie kind of dragging around this loose cart attached by ropes. And then sort of the most difficult one we had was this carrying pole example, where we have these 2 5-kilogram weights sort of swinging on the ends of each pole, and then sort of trying to simulate Cassie carrying this jug of water. And we found that just by throwing these, at the learning and having the learning see it during training, it handles it perfectly fine. And so we're able to learn policies for each of these models, both in simulation and then actually transfer them to the real robot as well. And can actually learn to stabilize even with these, big swinging weights on the side. We were also able to learn a single policy that could generalize to all of these different loads. So in this video here, the exact same policy, exact same neural network is being used to control both the left and the right, and can handle, different kinds of loads as well. So, this is one of the great things about data-driven policies. If you have a new task or some new environment, you can kind of just throw it at the learning and, through tons and tons of experience, it can kind of learn to deal with it. The other thing that we wanted to look at was starting to look at different terrains and start to not just be concerned with just flat things, but, uneven terrains and maybe even specifically stairs. So again, kind of just throwing it at learning using the same learning framework, but now in simulation show the policy all these different kinds of stairs, and we randomize basically the width of the stairs, the height of the stairs, how many stairs there are, and then like the slope of the ground after the stairs happen. And we find that again, amazingly the policy can handle it. And I'd like to point out that Cassie is still completely blind here. So even though Cassie can't see anything at all, just by experiencing all of these things in simulation over and over and over again, the policy learns to kind of just, handle it. And so because of that, you'll see that it doesn't actually quite step perfectly on each step. It doesn't step on the stairs exactly like we do, with, one foot on each step. It might, misplace a step, kind of just get the toe on one or just clip a step, and then kind of recover, fall back, and then readjust and then try again. And that's just like a product of the robustness that the policy learns just by seeing these things over and over and over again in simulation. So a really great video that I like to show here. So you can see that, like, Cassie's gonna miss a step right about not here, this next one, I think. So you'll see the right toe doesn't quite make it and just kind of clips, the edge of that step. And so it's going to start to fall backwards here. And you think it would fail and fall down, but it's actually learned to just kind of absorb that impact, recover, and then just try again. And it's just going to keep chugging along until it eventually successfully makes it up the stairs. And this kind of robust behavior is not something that we ever really have to specify it doing. It's just something that the policy finds because it's seen it doing training and it's always asked to, successfully walk up over the stairs. So again, we can kind of get many different sort of diverse and robust behaviors just by throwing them into training, and the policy will turn out fine. Some other really fun things that we've done recently, continuing to push the limits. We started thinking about longer term deployments and practicality and really testing the robustness of our policies. So we ran a 5K outdoors. It took us, 53 minutes, which is not very fast. I'm sure all of you could run a 5K much faster than that. But it's really starting to get to the steps of just showing how robust these policies can be, and how, practical they can actually be outside of the lab as well. And doing this sort of actually raised a bunch of issues and challenges that we weren't thinking about ever doing the lab when we were doing experiments inside the lab. For example, we kind of ran into some issues with wear and tear physically on the robot. So we found like after running the 5K, the feet were just completely worn down due to how we were handling impacts and due to the behavior that the policy was finding. And we never really noticed that this was a problem when we're doing tests indoors, but now that we're walking long-term outdoors on hard concrete, it was just something interesting to notice. And then we also found that we had to sort of adjust our policies to produce much more conservative motions. So the general policy that we were having on the left here, for robustness, kind of produces much more aggressive behaviors of, trying to really stick the foot out as quickly as possible to be robust. But that would not handle well on harsh roads over a long trajectory. So we found that we had to adjust our policies by sort of, again, penalizing, applying large foot forces to try and produce a little bit more conservative behavior, as shown on the right here. And then another example of pushing the limits, not on the robustness side, but more on the side of performance, is we recently set the Guinness World Record for fastest 100-meter dash by bipedal robot. I think that'll actually be in that, book of Guinness World Records soon. And so this was, again, just using the same training framework, but all we're going to do is now restrict the sort of tasks that we're training over. Instead of, training for all bipedal gaits, kind of just train to run really, really as fast as possible. And so Cassie can run a 100-meter dash in about just under 25 seconds, which again is not super fast. We're not going to be beating Usain Bolt anytime soon, but was still just a really, really great achievement to see. And was just really fun to try and push the limits and see how far our learning framework could take us. Finally, I would be remiss not to do a little bit of seamless self-promotion. We have two papers here that will be presented here at Humanoids by two of our master students, Feng Zhao and Ryan, sort of looking at trying to get more agile motions out of the learning framework. And so we're interested specifically in sort of doing really aggressive turns. So if we're running out of speed, and then I say I want to turn 90 degrees now in just 4 steps. And we found that this is actually something that our learning framework couldn't quite handle. It would either always fall down, or it would turn at a much, much slower speed, take about double the number of steps that we were asking for. And so we found that we had to kind of turn back to using reference trajectories again. So we came up with a single rigid body model and an optimization framework around that to optimize turning trajectories, and then use those to train policies and deploy that at the real robot. So we're still finding out what the limits of our current learning framework is, and sometimes it's not as great as we want it to be. But we're still trying to figure out, how can we produce more agile motions? Thank you. I would like to acknowledge all of our sources of funding, and then as well as acknowledge all of the students in our lab who produced all of this great work. And I'm happy to take any questions.
Hi, I'm Joe from Medtronic. It's really cool to see the sort of progression, the things that you've learned along the way to get to where you are now. And I'm curious, not just where that's going, but specifically higher up the stack. You've done a lot of work on robustness, but there's still just someone with a joystick there. And it seems like it would be a waste just to sort of use like standard motion planning and say, oh, we have a really robust robot that's going to make it happen. Can we take any of the things that we learned and apply them to things like motion planning, navigation, those sorts of things?
100%. Yeah. So that's looking forward, something that we're really interested in looking at, and something that we're currently looking at. Yeah, specifically higher up at the control stack, and starting to think about how can we integrate, external perception about the world as well. So we're thinking about, sticking a camera on Cassie and using that, at least, in the beginning, some navigation purposes, but as well as, how can that affect the motion as well? So we're still investigating that. We don't have any quite good concrete answers. But I think as we were having this discussion in the morning panel as well, there's some really interesting questions there. How can external perception and such affect your motion?
Quick question while we set up there. You have a lot of work looking at like these reduced order models, and also you talked a bit about how to design reward functions. And I feel like the two are actually quite intimately connected, right? And especially if we tend to use reduced order models for more long-term behavior. And can you talk a little bit about, is there a difference between the kinds of reward functions you want to use kind of a short-term scale, like with the really aggressive discount factor, compared to the ones that you want to actually care about long-term?
Yeah, so I guess even when we have been using reduced order models and trajectories, we've still been relatively short-sighted, and we're just kind of using those as references to just produce some desired motion. But I think there's definitely this trade-off and this part that's really necessary in RL of like, you're finding this really tough balance between providing enough structure such that the RL can actually find something that's useful, but also not being so restrictive that you're basically just following the position trajectory and not really following the dynamics of bipedal locomotion.